Next up we have a keynote. I'm delighted to introduce Dr. Niccolo Somaschi. He's the CEO of Quandela. And his talk is titled From Quantum Acceleration to Quantum Value. Please join me in welcoming Niccolo.
Right. Good afternoon, everybody, and let me thank first, of course, the introduction, Malak and Olivier for allowing us to be here and present and, of course, pushing for the community. And I also would like to thank the previous panelists to raise the important points I will present in my presentation, which is heuristic, how we create value today, acceleration as we call it, but not to forget how we scale, how we face modularity, networking, focusing on the long term where quantum largest value is. So a few words about the company first that I represent is a quantum computing company with headquarters in Paris, France, that comes from more than 35 years work on a hard technology that is core of our quantum computers. We are more than 100 people, 4 locations worldwide, and we work a lot on science, engineering, and technology. And we work on the full stack. We create and we fabricate quantum computers, we fabricate qubits, the scale, and we create quantum processor that we deliver to HPC and data center alike. We have open source operating framework. We work on the cloud, and we work hand in hand with the community, which is crucial, and we know that without the community, without the user, we will not be able to reach the ambitious goal that we plan. So what's next? It's been a few years that finally now we can say it's assumed quantum is not if it's coming, but is when it's coming. And I want to give you some thoughts today and present you our work on how we build the value today. And our platform, instead of what was presented before, is based on photon. We use particles of light. You can see the main modules here that builds our quantum processor. We generate qubits, these flashes of light that fly at the speed of light through routing modules and integrated photonic chips, where the white dots there are our active controls. And by mapping these elements in a simple goal, we can operate all-to-all connectivity, operate logical operation on these qubits. And that's how we take these units, we scale their functionality, their performance, and we build modular platforms. But we have to not forget where we have to go. And where we have to go, it's sometimes a scary number to say, especially to the people that manufacture these machines, which is towards millions and millions of qubits, physical qubits that are then error corrected. And this is very simple graph, but really is what every quantum computing company has to keep in mind. Because if we go up to this number of qubits, we have to face a lot of challenges that you can see on the bottom, which are performance of qubits, fidelity, number of qubits, some other engineering performances for us, like module transmission. And we can then move from certain sizes and reach acceleration and reach largest value. And the logo here means what the processor need to implement. So we need to create qubits. Everyone now has qubits, cool, but they have to be good. They have to be many. They have to be in infrastructure that can scale. Can we build a quantum supercomputer with thousands and thousands of cryogenic systems? That's an open question. Can we manufacture at scale? Can we manufacture the components at the million volume per year? Not every technology can. And can we interconnect? This is a crucial way to scale and to reach the largest gap that we need to face to get to the millions of qubits. So let's start from here. What do we do today? We work hand in hand with end user, corporates, at university, with partnership, and with customer program. to define solution on use case. And here you see some of them. We have worked in the past 12 months. And what we do is to look at verticals. We look at the algorithms that run best in our platform, and then we discuss and we work hand in hand with the customer and look where the use case that can exploit that is. We don't just randomly pick up use cases. No, we look at what the machine can bring the most value. So we had an example on the finance sector with Crédit Agricole, on pharma with a quantum software startup based in Korea, in Cerebro. We work with Total on quantum chemistry, identifying polymer properties. We work with EDF on different use cases, on energy, infrastructure, modeling dams and pipes, and study when fractures arise. So it's very important use case, but also on optimizing energy grid or large network. And we also work on battery and chemistry use cases in material science. And most of them, they're based on AI and quantum algorithm hybridization, just because today is what we see fits the most value in the near-term machine that we have accessible. So one example is, for example, is the use case we have developed for BMW and Airbus on image translation. So the use case was the following. They wanted to translate images on landscape of the day, images of the night, to train their autonomous vehicle, flying or the route one. And the way we improve the system that was generating a lot of hallucination, a lot of spots of lights were not there, was to introduce a quantum annotation, quantum processor, data generated by our quantum processor that could feed the standard Gen AI model and get then images that had less hallucination than the standard classical one or the full quantum one. So we learned how this can work. We learned how in this complex system, hybrid quantum and classical, we could introduce some quantum dash that can actually help. And now we're looking forward and trying to scale and see if we can reduce the hallucination even further, can even reduce the number of trainings required, so to work on use cases where data are fewer. Another example was with Crédit Agricole in the finance sector. They had a use case called folding angels, where we had to predict the unsolvable accounts. And their model, based on large AI classification models, was giving a certain performance. So we came up with another way, a hybrid way, to introduce a quantum classifier next to their classical one, and it improved by 10% the results in their estimation. So 10% more precision, which is a very close to ROI solution. We also work on the hardware. We said we already deliver and deploy quantum computing system for HPC and data center. We have deployed two today in external private data center in OVH Cloud in France and Exaion data center in Canada. And these were the first deployed quantum computing system by European provider to private data center. And what I want to highlight here are the system we are building. You can see the 12-qubit machine, which is on the catalog today. We're also delivering to Euro HPC joint undertaking program to be installed in the French National HPC Center. And then the other two quantum processor, Camarus and Diadem, which are that we're going to be on the catalog for 2026 and 2027. What I want to highlight beyond the number of qubits is the number of quantum operations per second, which is the final real metric that pin to a direct use case, because it identifies the number of operations we can make with this processor. And by moving to 24 qubits in our architecture, we can move already to 2,000 quantum operations per second, which in other platforms correspond to hundreds of qubits. So that's the way we scale, and that's another parameter that we list in the column next to it, which is the delivery time. We fabricate and we ship systems, which are server-like, that can be plugged in a standard environment without requiring any isolation, thermal, non-thermal, non-mechanical, and non-electromagnetic. It consumes just a few kilowatts, like few kitchen appliances, and is available, we can already demonstrate, more than 90% time, 24/7, 90% time. And we have calibration performed every 6 months, which is another important factor for data center to integrate resilient type machine. And the qubits are good as everyone else. Now, what's next I want to focus is what really creates the large value. So how do we get there? We need photonics. That's the thing that is so clear that even other people like NVIDIA CEO is saying for GPUs to increase data transfer, to reduce power consumption, and to go faster, we need photonics. This is happening in supercomputing today, and it will happen for photonics, for quantum computing as well. As it was said before, we cannot squeeze millions and millions of atoms in one single vacuum chamber, nor single chips. We cannot have machines that can fabricate that. So we need photonic interconnects among different processors. And it can be even different platform, a different processor, ideally. So how do we do that? We need photons. But if you're aware of the type of qubits, matter qubit and photonic qubits, it's difficult to make them speak to each other. So matter-based qubits, they have the ability to create entanglement fast, certain speed, but it's on the go. Every time I push a button, I create entanglement. But because they're matter objects, they also suffer decoherence, and that's one important performance that we have to focus on. On the light side, on the photon side, there is no decoherence. The photon travels and don't care unless they are lost, clearly, but they keep their quantum property, like polarization, for example. But to perform entanglement is hard. So photon goes fast, we have to make them interact, and this is a probabilistic operation. So what it means now, if we take photons and we look at error corrections, it means that we have to generate complex states of photons. So the photons here are this orange circle, and the black lines are entanglement. And this is very hard to do, but this is what we have to do. So what you see there basically is a photonic logical qubit with this kind of notation. And because performance and processes are probabilistic, we can calculate and see what are today the technology to build so. We have to generate photons, and the most used way is via some nonlinear interaction in materials, probabilistic. You see here a circuit, that's the circuits that we require to create free photon entanglement. So you see a lot of components there to be used to do this operation. So if we look at the full set of operation that we have to make to fabricate the state, we can really count how many components we need. And this is based on the fusion architecture by other photonic players. And we see that just for a logical photonic qubit, we need millions of sources, millions of detectors, and millions of other integrated photonic components. That's clearly a lot of engineering, that's clearly a lot of work, that could push very far away the time we can build this machine. So the approach we work on instead is hybridizing the two systems. Why to choose? We can find a way to use matter-based qubits, use their property to generate entanglement on demand, but to generate also photons, which are then used to link this qubit together, and therefore have an intrinsically scalable and interconnected platforms. How do we do that? The main technology is what is the DNA of Quandela. We use artificial atoms, nanostructure, which we manipulate in semiconductors. So you see here in a microscope, scanning electron microscope picture, and hidden in between this semiconductor object, there is one artificial atom, so thousands of atoms that behave like one, which is trapped, is always there. We don't need to use laser place it. We don't risk to lose it. It's always there. And via industrial processes, standard clean room fab processes, we can fabricate photonic cavities, and you can see these layers, these are mirrored like a sandwich, like a millefeuille for the French people here, and we place this atom in this cavity. And what it means is that we can operate it and use it to extract at high speed, gigahertz speed, photons and entangle photons. So this is the main building block that is the engine of our modular and interconnected platform. In practice, this is a single photon source. It's a hybrid matter, a photonic qubit platform. It's a generator or entanglement on demand. That is also the main building block for networking different systems. So now, as you imagine, the exercise we did was to take these objects and then calculate how many of these we can use to fabricate that photonic state, that photonic logical qubits. And it turns out that we can generate entanglement on demand with this atom and photon process and use 12 of those systems to generate at once these full photonic logical qubits. So it turns out that we can use only 12 of those systems, 24 detectors, another 24 integrated photonic components to build the same object. And you can find the paper there. So what it means is that we can reduce by a factor of 100,000 the number of components required to generate this logical qubits. And we also gain in threshold for the efficiency required to generate it. So what it means now is that we can also manufacture at scale. So we have modularity, we have networking, and we can manufacture. Why? Because we use standard 3.5 semiconductor industrial components and machines which are used for the laser that are shining this hole. What you see on the top is an image of the semiconductor. You can see the tiny dots that are shining like an image we can take of atoms in the vacuum chamber, but those will still remain there basically forever. So then, with the processes, we can then select and fabricate on demand our devices and package them in a scalable way. On the operation side, we just use silicon photonics. Foundries, thousands and millions of wafer per year. This is something that's already powering telecom and datacom, is what NVIDIA's here was showing before, and we just make them quantum proof with performances that we require for our performances. So if we look then again at the image, now you see we have all the ingredients to move from the scientific exploration, which is already done, to embrace and push as much as we can with partnership with use case and hybridization with AI, the quantum acceleration part, and then move to scalability and networking to the large quantum advantage. So then I also took some time to put down all the qubits roadmap of other matter-based players that you can see down at the bottom, and that's the average curve I can see and we can see in these roadmaps. So there is asymptotic because clearly there is not yet a proof of networking. So it's really coming up of the roadmap that in order to scale we need something else, we need something more. I then took the few other announcements or roadmaps of other photonic players that can see, well, I will just build a full millions of qubit platform and you will see it popping up there and there. So their roadmap is basically something like that. Our roadmap instead is something between. And really this is something that our team modeled, playing with the performance we need of these components that I just showed you, and coming up with the number of qubits we can actually manipulate. And you can see these two steps that we have to face, these two scalable mountains, ones that we already done with some initial modularity, and then the next, of course, with performance and full networking. So this is the way we're going to do it, and this is how we're going to place Quandela in the quantum advantage regime. thank you very much. So I look forward to interact with the community and share the fact that we are here also with the team of Quandela to be part and empower the ecosystem in UAE and to provide the solution for the next years. Thank you very much.